Hello everyone, welcome back to the latest lecture session. We are going to talk about a new aspect today. It's about lime soda softening. So let's dig right in. I'm assuming most people would have had at least some inkling about what we are going to talk about today, lime soda, and then we are going to use that to soften the water. So first, what is the softening the water about, right? So that means the water is classified as hard for some reason. Yes. So when do we classify this water as hard and how do we soften it using lime and soda? So that's the primary aspect we are going to look at in this session. So why do we need softening? As in, what's the issue with this so-called hard water? So if I have hard water, it increases the amount of soap needed, right? This, I guess those who are regularly using hard water will not be able to see this difference. But in general, you have soap, again negative charge and such, the kind of ions that create hardness, positively charged, typically bivalent, and they form what is called scum. So whenever you use soap, enough lather or such does not form, right? That's one thing. And this is seen quite often in Indian bathrooms and such. You see scaling on pipes. Yes, sometimes the pipes or even the taps, they break off, especially the cast iron or metal pipes. Yes, that's something that you see. Yes, causes walls to stick, and walls that are not often used or maintained, they harden up and you can't really use them. Again, why is that? You have calcium carbonate crystals preventing free movement of that particular wall. And this is again pretty common in India, staining of plumbing fixtures, let's say. Again, in bathrooms and such, especially we see, at least in from where I come from, I used to see this, not in Roorkee though. So I guess the water there is relatively hard compared to the water in Roorkee. And I used to see this kind of scale that's formed on the taps or along the walls where the water used to drip. So this is due to precipitation of calcium carbonate, CaCO3, the solid, right? I think I have a picture here. So here you see what happens to scaling inside pipes. Maybe I should not have mentioned on, maybe inside pipes, right? So this is the pipe and you see calcium carbonate over time, right, precipitating out, right, and you see the cross-sectional area available is remarkably less right now. So this is something obviously you don't want. Now your pipes can't carry the water that it was designed to carry. The distribution network is going to fail. Other than that, depending upon relevant hardening and such, you can even have cracks in the relevant pipes. So this is what you see. So I should have also had a picture about stains on the plumbing fixtures, but for quite a few people in India, that's something they would have seen, right? So I don't want this to happen, right? Either this to happen or not do I want these aspects to happen, right? Soap and also leave stains on plumbing fixtures. For example, this you would have seen where, or people with dishwashers would notice this acutely, because you can measure the amount of anti-hardness or water softening agent you add. So in dishwasher, typically you have a detergent that's added. So obviously you are trying to form some lather, decrease the surface tension between your oily particles that are on your dirty plates and such. But if you have water that has high hardness, for this action to occur, you are going to have a requirement for a lot more detergent. So to prevent that and also to prevent scaling within the dishwasher, what do you need to add? You need to add what is called, sometimes they call this anti-scaling agent or softening agent, let's say, right? Why is this? They don't want to have this precipitation of calcium carbonate occurring on or within the relevant dishwasher, and also they don't want the soap to be consumed, let's say. So this is one thing, or one major reason why we want to have softening, right? So in general, in water and I guess also wastewater, we need to remove certain chemicals. We looked at the general aspects. In water, depending on where you are, you might need to typically remove these. In India, depending on where you are living, iron and manganese, yes, will have to be removed. That's relatively easily done with aeration step or an oxidation step. Arsenic, carcinogenic, and also non-carcinogenic adverse effects. So this depends upon and the need for removal depends upon where you are living in India. Hardness, quite a few places in India are affected. Nitrates too. Radionuclides not very much. Organic chemicals, nowadays we see that the requirement to remove that is increasing day by day with different kinds of what we say stresses on the surface water bodies. In wastewaters, it can be anyone, any chemical, especially let us say if it is from an industry, yes. But in general, we are concerned with metals and organic chemicals. For example, we have Patanjali nearby here, and they have a thriving FMCG, I guess, business out here, and they are going to have organic chemicals in their wastewaters. They need to be degraded. So, it depends upon the kind of wastewater. But in this course, obviously, we were looking at sewage water, let us say, not industrial wastewater. That is something I wanted to point out. So, hardness, right? If I want to identify hard water, what are the two ways that we can typically do or understand, I guess. So, soap, you need a lot of soap to form leather. Why is that? Calcium and soap, you have this scum being formed, let us say, right? And thus enough soap is not available for use for decreasing the surface tension or such, if I may say so. Thus, you have to be able to add more soap than is necessary when there is little to no calcium or the relevant cation present. And another aspect that you would have seen is, I think I mentioned this earlier. Earlier we used to boil, or maybe I am sure even now people boil it, boil water in their homes for various reasons, either for bathing or for drinking water related disinfection, I guess, right. So, then after some time you would have seen scales being formed along the sides of the relevant container, and you would see that over time a lot of energy has to be put in, or relatively more energy has to be put in to be able to cause the water to heat up by the same, what do we say, amount of temperature, let us say, right. So, for the same temperature change, you need to heat it up for a lot more time. So, you are putting in more energy per change in temperature. Why is that? Because now you have these scales which are not great conducting agent of heat, or not good conductors. So, the water here, I guess, experiences inefficient heating. So, that is something most people in India would have seen. So, then you can say that your water is hard, let us say, right. So, again, as you can see, household applications and obviously in industries too, you are going to see scaling and relevant issues or adverse effects in boilers and such, let us say, right. That is something to keep in mind. So, this is from what do we say, just what do we say, looking at the relevant surroundings where the water is used, right. So, as can be seen from the equation previously, typically we are talking about cations, and in general though we are concerned with the bivalent or divalent cations. Typically they are the metal ions, and what are the usual, not usual, some of the probable metal ions, I guess calcium, magnesium, iron, manganese, and maybe is the strontium, okay. But in general not present a lot, or at least iron and manganese are removed pretty well or in a different way by aeration and such. But what is usually present because of the calcite or dolomite deposits in the groundwater and such is calcium and magnesium. So, when I am talking about hardness, I am typically concerned about, or I talk about calcium and magnesium, right. So, that is something to keep in mind. It can be trivalent what do you say, cations too, but they rarely exist in our waters of interest, if any, if they exist. And calcium and magnesium are the usually found bivalent cations that contribute to hardness in our waters, let us see. And where do they come from? They come from calcite and dolomite deposits in the subsurface, let us see, right. For example, I think I remember reading that calcite, source of calcium, accounts for almost 4% of the earth's, I think, maybe crust, and dolomite maybe 2%. So, you get an idea about the relative abundance. So, groundwater or water which has been in contact with these deposits will have considerable, what do we say, calcium being formed. But again, so if what do we say, the relevant calcite is a solid, why will it dissolve and become or release these calcium ions or magnesium in the case of dolomite into the water? Why or what happens? Let us look at that. Okay, so I have precipitation, yes, and this is in contact with maybe carbon dioxide or any other gases in the atmosphere that can lead to decrease in pH. For example, carbon dioxide, when it dissolves, let us say this is in the gaseous phase, as rainwater droplet comes down, carbon dioxide in the gaseous phase will dissolve. So, carbon dioxide in the aqueous phase, right. So, this will be in equilibrium with H2CO3, let us say, or you can directly say that carbon dioxide in the gaseous phase will be in equilibrium with H2CO3, right. As you can see, CO2 plus H2O goes to H2CO3. So, this is what it typically exists as, let us say, yes. So, H2CO3 again an acid, not a strong acid, but enough, what do we say, the pKa is less than 7, right, and depending on the concentration and such, the pH of your rainwater will be relatively less. So, this is relatively acidified rainwater, let us say, will come into the relevant, what do we say, will permeate through the soil. So, some of it can be neutralized based on the different bases or such, but some of it will react with these deposits, let us say, yes. So, if it reacts with calcite, so it will make the system, or it will see to it that the calcite dissolves. Earlier it is in the solid phase, as is evident by this particular subscript, S for solid. So, but after addition of this or coming in contact with slightly acidic water, it forms this particular compound, meaning in effect it will say it will come to this. So, as you can see, what was earlier a solid is now dissolved into the water. So, thus you can see that the relevant compounds calcium and magnesium are released into the, what do we say, subsurface or groundwater, right. You can see how that comes about. So, here we talked about carbon dioxide as one aspect, but there will be other gases that can decrease your particular pH of the rainwater droplet, leading to dissolution of your particular deposits, right. So, that is one aspect. So, here we see calcium and magnesium being released into the subsurface and increasing the hardness. Some basics before I go further, maybe I should have even discussed this earlier, but I would have assumed that you know about this earlier, but as a refresher we will just talk about some of the basics which we have to look at, or maybe have some understanding when we look at these what is it now, lime soda based softening of hard water, let us see. I think some of these aspects we did discuss earlier. For example, if there is a metal, let us say, and I think we talked about this in the context of coagulation and such, we were talking about Fe3 plus, Al3 plus, Fe2 plus and such, let us say, right, electron deficient. Again, metals, when I put them into water, they are not going to be present only as water, they will form complexes, and complexes can be OH minus electron rich, NOM again electron rich, and other ligands that are present in water, let us see, or some of them will also precipitate out into different solids, right, they will precipitate out. But for precipitation to occur, a threshold has to be reached, as in the solution has to be super saturated. Just being saturated does not lead to precipitation. So, I have compounds, let us say Ca2 plus and CO3 2 minus in water, and I know that the compounds can precipitate out as CaCO3, right. For example, this can be in equilibrium, but for this to occur, right, these either of these should be relatively high, right. Again, the system should be super saturated. Again, we are not going into that right here, but you can look at the other NPTEL courses about environmental chemistry, let us see. So, that is one aspect again. So, we have metals that are soluble as free metals themselves and exist as free metals. We have complexes which are again soluble, but again keep that in mind, maybe not greatly relevant in this process. But another aspect that is relevant is that you will have precipitation in the form of solids, let us see. So, the solid is not in the aqueous phase, so you can remove it, right, either by sedimentation, filtration or different means, let us see. Typically sedimentation is practiced after coagulation and flocculation to remove the solids in the context of lime and soda softening. So, here I want to talk about acid base chemistry. I think the best one to talk about is the acid of relevance here. Let me see if I have another picture there. Okay, I will come back to that. So, I have H2CO3. This is an acid, as you can see, it can be a proton donor. Again, different definitions, but here we will stick with the one that talks about proton donor, let us see. So, this can be in equilibrium with H plus and HCO3 minus, yes, and HCO3 minus can be in equilibrium with CO3 2 minus, bicarbonate, H2CO3, carbonic acid, bicarbonate and carbonate, right. Again, you do not need to look at the name, CO3 2 minus and such. So, what do you see? H2CO3, right, can dissociate into HCO3 minus and give out a H plus. HCO3 minus can further dissociate into CO3 2 minus and give out H plus. Let us say there is a system or water where these three compounds H2CO3, HCO3 minus and CO3 2 minus, which I refer to as the carbonate system, are at equilibrium. So, let us say there are different particular or three particular aspects here, and if I remove one of them by different means, let us say, then again the equilibrium is disturbed, and then there is going to be a rearrangement of the concentrations or the H plus, such that you have a new equilibrium that exists between these three compounds, let us see, right. So, that is one thing to keep in mind, but when I say acid, what is it doing? It is releasing H plus, but you would have heard about strong acids, let us say HCl going to H plus and Cl minus. So, why is it that HCl is referred to as a strong acid, but maybe not H2CO3? Why is that? Well, it depends upon the pKa and its ability to release the H plus. For example, for H2CO3, I think we looked at this graph. This is called the speciation diagram. So, here I will have the relative concentrations or concentrations on the x axis, I will have the pH, and what else will I have here? And here I will have HCO3 minus profile, and here I will have CO3 2 minus profile. Let me write them down. So, this is CO3 2 minus, yes, and the other one that is predominate in this region is HCO3 minus. The one that predominates out here, I guess, is H2 CO3, right. So, as we discussed earlier, this point where both the protonated and deprotonated forms of the acid are at the same concentration is called the pKa 1 for this case, because there are two pKas. This H2CO3 can give out 2 H plus, so it is pKa 1 and pKa 2. The name is self-explanatory, or the term is self-explanatory. pKa 1 is the acid dissociation constant, acid dissociating, right, H2CO3 dissociating into H plus and HCO3 minus. So, this is 6.3 and this is 10.3. Again, you do not need to mark these up, these will be given if and when required, right. So, this is what I have. So, as you can see, if the pH is around 4, let us say, somewhere out here, right, if the pH is around 4, let us say, fine. If I add H2CO3 when the pH is at 4, as you can see, most of it will stay as H2CO3 and very little will dissociate to form HCO3 minus. Why is that relevant? Because as you can see here, only when it dissociates will H plus be given out. So, at pH 4 very little will dissociate, right, very little. You can look at that, I think 6.3, 5.3. So, less than 1% will dissociate. So, when I add H2CO3 at maybe 5.3 or less than pH of 5.3, as can be seen from here, most of it will stay as H2CO3, it will not affect the pH of the system, because H plus can't be released or enough H plus can't be released. But if the pH is around, let us say 8 or so, right, in this region, as you can see, any H2CO3 that is added will mostly stay as HCO3 minus and very little will stay as H2CO3. So, that can bring down the pH. Why? In the process of H2CO3 dissociating into H plus and HCO3 minus, you are going to release the H plus and thus bring down the pH. So, same case here at different pHs and pKa values, right. So, whenever we are talking about strong acid or weak acid, what am I concerned about? I am concerned about this acid dissociation constant for the relevant acids. So, for HCl it is 0 or such. What does that mean? Or less than 0, but for practical or for illustration purposes, I am asking you to assume that it is 0. So, what does that mean? So, at almost all pH ranges, HCl will always give out H plus into the solution, meaning it will be able to affect the pH of the solution, right. So, that is something to keep in mind. So, this is called a speciation diagram, right, where we look at the concentration of the relevant acid base species and their change with pH, let us see, right. So, that is something you will have to keep in mind, because we will use this later. So, what is this other aspect? We talked about pKa and we talked about speciation diagram, but looks like I should have talked about another aspect before I skip to pKa. So, let me talk about any equation that I have here. Okay, fine, I identified the equation that I want to talk about. This is the equation that I want to talk about. So, you have a reactant that is in equilibrium with products, right? The key is at equilibrium. So, there is a relationship or a constant that will that depends upon temperature and pressure, which can give me an idea about the relative concentrations of the products to the reactants if the system is at equilibrium. So, for this equation I will have something called an equilibrium constant. So, what is the equilibrium constant for this equation? I will write that out here. It's, or let me write it here. So, we are talking about equilibrium constant, right. So, what do I have? The equation I am considering is H2CO3 in equilibrium with H plus and HCO3 minus, right. So, the equilibrium constant Ka, let us say I will call it Ka1. Typically, it is written as capital K, that is enough, but because it is for acid dissociation, I am using the subscript Ka and 1 because it is the first one, but for now we will just suffice ourselves to or limit ourselves to capital K. Capital K is nothing but the activity, or let us say, let me not call it activity now, the concentration of the products. As you can see, the products are H plus and HCO3 minus raised to their stoichiometric coefficients, but you see stoichiometric coefficients here are 1 H plus and 1 HCO3 minus divided by the concentrations of, or activities rather, which we are assuming to be concentrations here, right. This is key, we will talk about that later. Actually, it has to be activity divided by the concentration of H2 of the reactants raised to their stoichiometric coefficients. So, K is, on the top you are going to have the product of the concentrations of the products raised to their stoichiometric coefficients. In the denominator you are going to have the product of the concentrations of the reactants raised to their stoichiometric coefficients. So, more or less products by reactants, that is the equilibrium constant. So, this is applicable obviously, as can be seen when the system is at equilibrium, right, as in when the system has been given enough time to go to the furthest extent possible under those temperature and pressure conditions. So, that is the equilibrium constant, yes. So, for this again these constants are measured, you can get them too from delta G values, and most of these constants are measured, or almost all of them that are known to the usual world are measured. So, you can use these constants and play around to get your relevant values. So, the pKa2, right, it is similar to pH. pH we know is minus log activity or concentration of H plus, right. In this class though, we are always assuming activity of the compound is equal to concentration, and the pKa value is equal to similarly minus log of this Ka. This was Ka, right. So, pKa is minus log Ka. So, that is something that gives you an idea about the relationship between the products and the reactants, let us say, right. So, that is something for you to keep in mind for the other aspects we are going to discuss. And what else did I want to discuss? Okay, acid base, we looked at that, right. Acid can give out a H plus, base can take up a H plus. So, in this case HCO3 minus can act as a base by taking H plus and going to H2CO3, or HCO3 minus can act as a acid and go to CO3 minus by releasing H plus. It all depends upon what pH is prevailing, right. That is what we see here, yes. And precipitation. So, depending upon, okay, this is a figure that I wanted to have. So, here we are talking about Fe2 plus total, it is not free metal, Fe2 plus total is equal to 10 power minus 4 molar. This is a log C pH diagram. Here we have log and here we have pH, let us say, right. When we say log, so if it is 2 and 3, we can more or less forget or assume that whatever is at 3 is much smaller than the one at 2, let us say, right. So, log C pH diagrams, let us say. So, what does this tell you? It tells you that at different particular pH and different concentrations, right, different pH, different concentrations, Fe2 plus can stay as metal, right, or it can stay as a complex, yes, or it can also precipitate, right. So, this is, or in this range it can also precipitate, right. Similarly, in our case also, okay, let me just look at this particular aspect for now. So, what do I have here? This is called, for precipitation, we write it as solubility product. FeOH twice solid, right, will be in equilibrium with Fe2 plus and 2OH minus, right. For this, again, equilibrium constant, what is that equal to? It is equal to activity of Fe2 plus into the activity of OH minus. It is always products by reactants, again stoichiometry coefficient, by activity of the solid FeOH twice the solid, right. But as I mentioned, in general in this class, depending on the, assuming that the solutions are low ionic strength, we are assuming that activity can be, what do we say, represented by concentration. So, here one aspect to keep in mind is activity of solids. Again, we look at it as mole fraction, it is going to be equal to 1, assuming it is a pure solid. So, whenever you have solid in this equation and you are looking at equilibrium constant, you can think of that as being equal to 1, let us say, right. So, activity of this FeOH twice solid is equal to 1. Same case with water. If ever you see water in either the reactants or the products, either the reactant or the products, H2O, and because everything is in water and we are talking about mole fractions, infinite dilution, it is also equal to 1. So, you can neglect them. So, in essence, this equilibrium constant equation for the equation above will just be activity of Fe2 plus, which I am representing by concentration, into, this is 2 plus OH minus raised to the power of 2, right. This is called the solubility product. As you can see, the metal, or the solid, pardon me, is, so what do we say, dissociating and becoming soluble, let us see. So, this is called the solubility product when we write it in the form of the solid dissociating, let us see, or dissolving. That is why we have KSP, let us say, K solubility product. Again, this is similar to the, or this is the same as the equilibrium constant we discussed. So, for acids we call it as the acid dissociation constant. For solid dissolving we call it the solubility product. So, these are aspects that you just need to be aware of. And in general, as you can see, when will this particular solid be formed? As you can see here, you can also see that in the relevant equation, not equation, in the graph. So, when will the equation go from the right to the left, or the reaction, pardon me? That will happen when Fe2 plus or OH minus are high, or both are high, right. So, that is what you see in this graph also, when pH is high, meaning OH minus is high, and also when Fe2 plus concentration is high, that is when this solid will precipitate out. So, obviously, as you can see that there are certain thresholds, again that depends upon the relevant solubility products and such, beyond which the metals or the relevant cations or the bivalent cations or such will start precipitating out. So, this is the background that you need to be aware of. What is it? So, we know the pKa, we know the speciation diagram, and what else? We looked at equilibrium constant, we looked at solid precipitating out, and for solid, how to write this equilibrium constant related equation and such, let us say, right. So, with that I will end this session, and in the next session, using these particular basics, let us see how we are going to apply them to be able to remove this calcium and magnesium which are in water and which are causing relevant issues, to my engineered distribution networks, or whenever I use water, right. So, thanking you for your patience, I am going to end this session.